everyone, and welcome to our video on Objective 1.7 and 1.8. I am going to split this probably into two videos because I want to be respectful of you guys' time and workload right now. And I think if I tried to do the whole thing, it'd be over the 20 minutes. So please make sure you pay attention for this one. This is something we talked about last year, but I'm really going to focus on how AP wants you to answer these questions and the vocabulary they want you to use. So like when we talk about periodic trends, if they ask you, why is, see a periodic table, potassium larger than sodium, you can't say because atomic radius increases as you go down a column. Okay, that's not an explanation, that is the trend. So you have to use your chemistry knowledge to explain trends for this. Okay. Oops. So the first thing, if we're going to be talking about periodic trends, what the heck is periodicity? Periodic trends, what are they? So these are going to be our chemical and physical properties that are dependent on our valence electrons. Okay. When we look at the periodic table, it is beautifully arranged according to their atomic number, which means that there is a regular change in valence electrons as you go across and down. Meaning that atoms that are in the same column or family are going to have similar properties because they have the same number of valence electrons. Our first group, so this is going to be really more Objective 1.8, which just has to do with valence electrons and the ions that are formed, okay? These are things that we definitely talked about last year, but really I just told you the numbers to put over the columns on the periodic table. So this is the why behind those charges, okay? So noble gases are not going to form ions, at least not very easily. And that is because they have their outermost S and P orbitals already full, meaning it really doesn't want to gain any more electrons and it really doesn't want to lose any more electrons. So you would have to add a ton of energy to force it to do those things. So your group 18, which is your far right column, your noble gases are going to be relatively inert, which means unreactive, and they're going to resist the loss or gain of electrons. All right, then we're going to talk about our first two columns. So you do need to know the names of our columns of our families. So the alkali metals are going to be that first group, group 1. Okay, the group 1 atoms all end in some kind of S1, whether it's 1s1, 2s1, 3s1. What that means is that in their outermost energy level, they only have one electron. So the easiest way for them to form a noble gas configuration would be just to lose that one electron. If it loses an electron, it forms a +1 ion. So our first group, called alkali metals, are going to form +1 ions. Group 2 is right next door. It only has 2 electrons in its outermost energy level. And therefore, just like with alkali metals, it is easiest to lose them than to fill up the rest of the energy level. So it's going to form our +2 ions. Those are the alkaline earth metals. Group 2 is called alkaline earth metals. Group 16 and 17. So group 16 is your oxygen group. It is going to have an electron configuration that's going to end in something with S2P4 for its valence electrons. That's pretty full. So instead of losing all 6 of those electrons, it's much easier for it to gain 2 electrons in order to have a full outer shell. So if it gains 2 electrons, it's going to form a -2 charge, just like our oxygen does, just like our sulfur does, and so on. Okay. Our group 17, you do need to know those are called halogens. So group 17 are our halogens, our fluorine, chlorine, iodine, bromine, the good stuff. They end in S2P5. Again, that'd be crazy to try to lose all those electrons. It's much easier to gain 1 electron. So those are going to form ions with a charge -1. Once they've gained that electron and have that charge, they now have a noble gas configuration. So that is essentially your Objective 1.8, the valence electrons and ions objective. These are things you knew from last year. This is just the more AP style explanation of that. Our trend we'll talk about today is ionization energy. Okay, so in order to talk about ionization energy, we need to define it. So ionization energy is the energy it takes to make a mole of your +1 ion, or to remove a mole of electrons from your neutral atom. So you're going to, and they do have to be gaseous. So you're going to start out with your atom in the gaseous state. You're going to put in energy, and ionization energy, which is going to remove an electron, leaving a positive charge. Okay, and they are going to give, let's move my face, you that energy in kilojoules usually per mole, which means it's not the energy to remove just one electron from one atom. It's going to be the amount of energy it would take to remove a mole of electrons from a mole of the atoms. Okay. If you were dealing with a second ionization energy, that's going to be the energy associated with removing that second electron. So you'd start with a positive ion, and you'd be removing one to form a 2+ ion. These are going to take energy, making it endothermic. You have to add energy to the system to take away those electrons. Okay. All right. Okay, so this is back to Coulomb's law. So we are going to discuss the magnitude of ionization energy based on Coulomb's law. So the higher the nuclear charge in general, the stronger the electrons are held, the higher the ionization energy. Okay, so more protons means they're holding those electrons really tightly, means it takes a lot of energy to take them away. The other factor in Coulomb's law is distance. So the larger an atom gets, meaning more energy levels, the further the electrons are away from the nucleus, and therefore the lower the energy associated with removing that ion or that electron. We call this the shielding effect because those inner core electrons are going to shield the outermost electrons from feeling that nuclear charge. Okay, so as you increase distance from the nucleus, you are going to decrease your ionization energy. Again, we and you guys had no problem last year, and this was during quarantine, but you guys had no problem last year determining that as we go from left, or memorizing, that as we go from left to right, ionization energy increases. It was something you just memorized, okay? But this year it's really important that you're able to explain it. Very rarely would the question just ask for increase or decrease, okay? So, and you can't say because ionization increases left to right. You have to say, as you move from left to right across the periodic table, the nuclear charge increases, causing the ionization energy to increase because electrons are held more tightly or more strongly. All right, you could even say because of Coulomb's law, the increase in positive charge with the same distance increases the ionization energy. And notice that the distance is essentially the same when we're talking our electrons from left to right because we are in the same energy level as you go from left to right. All right, as we go down the group, our ionization energy will decrease because the distance from the nucleus is increasing. So while there is an increase in nuclear charge, there is also an increase in distance, and that increase in distance is going to be more important than your increase in nuclear charge. So because those valence electrons are shielded from feeling the core because of their distance from the nucleus, they are going to have lower ionization energies. All right. Successive ionization energies. So successive ionization energies is going to refer to like second and third ionization energies, because we can remove more than one electron from an atom, and it's going to get more difficult every time. It's going to get more difficult every time for a few reasons. One, you don't have as many negative charges repelling each other. So if you had, let's say, 6 electrons in your valence shell, and you wanted to remove the first one. Well, there were 6 electrons pushing each other away, so it was X amount hard to remove that electron. Well, now you only have 5 electrons pushing each other away, which is less repulsion, so it's going to be even harder to remove another one. Okay. Also, once you've removed one, that positive pull from the nucleus is pulling on fewer electrons, so they are feeling more attracted to the nucleus. So that's pulling them closer. The closer they are to the nucleus, the higher the ionization energy. Okay, so no matter what your first ionization energy is, you know that your second one is going to be higher than that, and you know your third one will be even higher than that. And there's a cool trend that if you look at your successive ionization energies, you can determine how many valence electrons there were. Because valence electrons, which are in that outermost energy level, are going to be much easier comparatively to remove than what we call core electrons. Core electrons are everything that's not a valence electron. So if you look at this chart, and it's a little blurry, but I think we can still use it, you can see that sodium has 496 kilojoules per mole to remove that first electron. Then that second electron is like 10 times as much, okay? And then there's more and more and more for each one, but the big jump was between that first and second ionization energy. What that means is your first ionization energy got rid of your valence shell. The second ionization energy started digging into the core electrons, okay? Same thing here with magnesium. So we have an ionization energy, we have another one, and then a much larger jump between our second and our third. So that is indicating that you have left your valence and gone into the core. Aluminums. And then, holy crap, from 27 to 11,000. Okay? 2,700 to 11,000. So you can see that your big jumps are corresponding to the number of valence electrons. We know from the periodic table that aluminum has 3 valence electrons. When you get to that fourth removed electron, you've gotten to the core. Okay. Sulfur. So we remove 1, 2, 3, 4, 5, 6 with similar magnitude numbers, and then we jump from 8,000 to 27,000. Okay, so that tells us that sulfur must have 6 valence electrons. So they'll use this information a variety of ways to get you to maybe predict what kind of compound something would form, or predict what kind of ion it will form. Or it might just ask you from this multiple choice list, and based on this chart, element X must be what? Okay. So we're going to try a few. So the first one I need you to try, you're going to have 2 parts here. So you're going to give a brief but complete explanation of the changes in ionization energy as the following transitions in the periodic table are made. I am going to have you just do A here. Okay, just A. As you go from magnesium to strontium, I want you to explain, using the terms we've learned here, why and how magnesium to strontium changes. So we're going down a family. So give your explanation. Okay, part B. Now I want you to give your explanation as you go from sodium to argon, which is across a period. Okay, what happens to ionization energy and why? Okay, for this one, we're looking at, so we have our ionization energies, our first, second, third. This chart looks a little different than the chart that was in the notes a few slides ago, but as we've learned with AP things, they don't always look identical, so I wanted to show you a variety of ways to look at it. So element X, you can see their ionization energies, and only the first through third. For element Y, you can see the first through six. So in our first question here, we're going to answer question A. In which group is X likely to be found? And for the group, you can put what we call it or the group number. For B, in which group is Y likely to be found? And then there are only 3 ionization energies listed for X, suggest a reason. So if you saw this on a test, what is one reason that you could see that discrepancy? Okie dokie. That's it. Tomorrow we'll continue on. We'll talk about atomic radius and electronegativity trends.